What happens if you leave your iced drink out on a hot, sunny day? Well, it warms up, right? Of course. But how it warms up can be a little counterintuitive. Let's warm up to this idea. This is Real Chem. It is pretty common to face counterintuitive ideas the more we learn. And this is okay. It's the same for everybody, but it just takes persistence in following the logic. Heating and cooling curves, which is our focus here, are a good case in point. Let's explore. Temperature is related to the kinetic energy of the particles in a substance. A higher temperature corresponds to a higher kinetic energy. In a solid, the kinetic energy is attributed to the vibrations of the particles. However, attraction between the particles is what holds them in place. When you heat a substance like ice, for example, the particles vibrate more rapidly and their kinetic energy increases. This is seen as an increase in temperature, which we can measure with a thermometer. Upon further heating, the particles gain enough kinetic energy to partially overcome the attractions holding them in place. The particles can now move from their fixed positions, and the substances change from a solid to a liquid state. While the substance is changing state, the temperature does not increase even though it is heated. This is because the heat energy is being used to overcome the attractions between the particles and not to increase their speed. A heating curve is a graph that shows the temperature of a substance versus the amount of energy the substance has absorbed when heated. Let's do a heating experiment. Step 1. Ice at -10 degrees Celsius is placed on a hot plate. Step 2. The hot plate is turned on and heat energy is added to the ice, which increases the kinetic energy of the particles. The particles vibrate faster and the temperature increases. If heat is added at a constant rate, the temperature of the ice increases at a constant rate until it reaches 0 degrees Celsius, or its melting point. Now, step 3, heat continues to be added, and the ice begins to melt and become water. The temperature does not increase because the heat energy is being used to overcome the intermolecular forces between the particles, not to increase the speed of the particles. Step 4, once all the solid ice has become liquid water, adding more heat causes the temperature to rise again. Kinetic energy increases and the water molecules move more rapidly. At 100 degrees Celsius, the water begins to boil and the temperature remains constant. The kinetic energy of the water molecules is now large enough to completely overcome the intermolecular attractions, and the molecules spread farther apart. Note that the horizontal line corresponding to boiling is much longer than that for melting. This shows that much more energy is required for the water to steam transition than for the ice to water transition. Much more energy is required for a substance to boil or fully overcome intermolecular forces than to melt or partially overcome intermolecular forces. In more formal terms, a substance's enthalpy of vaporization is much larger than its enthalpy of fusion, which is an older term for melting. A cooling curve shows how the temperature of a substance changes with time as it is allowed to cool. It is the reverse of a heating curve. During cooling, the kinetic energy of the particles drops, and therefore the temperature reduces. Like in the heating curve, the temperature remains constant during the change of state. This is because the drop of kinetic energy during cooling is counteracted by the energy released by forming intermolecular attractions in the substance. Heating and cooling curves make sense once we bring together what else we know about energy and bonding. They also tell us that on a hot summer's day, we can leave that drink out for a while. but we do need to get back to it before all the ice is melted. After that, it's going to warm up quickly. So explore and remember to have fun.